Okay, welcome to Cal 2. I recognize almost half of you, which is a good thing. My name is Robert DiGiovanni, and I'll be the instructor. And I'm hoping already that you found your way into Canvas and that you know how to get there. Anyone not know what I'm talking about here? Everyone's comfortable with that? All right, so I'm going to go ahead and log into your course. I'm not going to go through the syllabus or anything. Just want to make sure everyone's aware of what's there for you. If Canvas is even working today, we'll see.
It's the first day.
There we go. Okay. So I don't know how it is as a student, but I know for me, anytime I log in, I always have to change that semester.
Yeah.
And they told us about a year ago they'd fix that. So they're still working on it. So this is section 12, 2414 section 12. And if you go here, then we have our main course page. And I have an assignment for you that's due, see, 2 days. So by the end of class, well, no, we end at about 10:40. So at 1 o'clock this Thursday, I need you to click on that link. I need you to take what's called the syllabus confirmation quiz. Just means that you've read the syllabus, you understand the requirements of the course, you've had an opportunity to ask questions. And there's an orientation video. So let's see, show of hands. How many of you have watched that? Okay, it's kind of long. Yeah, it's an hour long. An hour, really?
It is 55 minutes.
Yeah, I don't know. I just was dragging on, just on and on and on. But it's basically what I would normally say in class the first day, but there's no sense in wasting an hour of class going over things like that. But there are important details in there that you need to be aware of. So make sure you watch that. We have our course schedule, which I'm going to be covering, or that's the plan for me to cover this semester. And then the camera in the room is going to be here every day, and if everything works out technology-wise, and I'll be recording all my lectures, and I'll post them on YouTube. And to get to them, you can just click on this link, and it'll take you to YouTube. In fact, let me go ahead and just click on it, make sure it works. And let's see here. Yeah, so this is my 2414 Cal 2 Tuesday, Thursday, 9 a.m. Spring 2017 playlist. And you'll see in here the videos, they'll appear. And I don't know how I'm going to put them in there. I might just put like day 1, 2414, Tuesday, Thursday, 9 a.m., day 1, then day 2, day 3, day 4. There might be 2 videos for each day because this automatically will partition a video. I forget why it does it. I think it's an hour. At an hour, it automatically splits it into 2 videos. So it might be 2 videos. Just be aware, okay? And so the idea of the video is not so you don't come to class. It's so you can pay attention in class and ask questions. And you may, I don't know about that seat. Just maybe slide the table over just a little bit. I just don't want you, if you mess the camera up, then, someone goes to watch the video and then the camera's like pointed over here, So.
He hasn't had breakfast, so he'll get hangry.
So anyways, the videos will be there, and come to class. I still take attendance, but it's just something you can go back and reference if you need to, all right? And then along with that, the other important part of our, what is going on here? Yeah, that doesn't look good. Does that look like a Firefox issue? Not responding. Firefox is not responding. Oh.
Something's clicking at the bottom.
Okay, so, that's the problem. Okay, so then we have not only our lecture videos, but we also have some videos that I already made. So for all of your homework problems that I assign in class, or for a majority of them, maybe not all of them, I have solutions to the videos, just me up there working out the problems. So The idea is that if you're at home, you're doing your homework, you're stuck, you have the video to go to. And historically, my students have said that's the most useful set of videos I have, or the homework solution videos. So, yeah, that's it. So I'll let you watch the orientation video. I don't want to bore you with details I'm going to cover in that video. Any questions? Yes?
For anyone who doesn't know, would you mind explaining where your office is?
It's on the first floor of this building, and so you have to go out to the elevator shaft area, staircase, go all the way down, come back in the building, which means you'll be outside, okay? And you have to come back in, walk all the way down to room 111A, go into 111A, navigate through the corridor, and then you'll find my office is 1110. So it's like down the hall on the right-hand side.
The one that's always dark.
Yes, it's dark. I've got like this, what do you call that? No, on the windows I have that privacy glass type stuff that you can't really see in. It's usually dark in there. I even have a note on the door that says even if it's dark, like knock on the door because I'm probably in there. So my office mate and I, we're just kind of like, I don't know, recluses, I guess. Yeah, we just chill out. So anyways, yes, so that's where my office is. And why would you even need to come see me? I'm not sure. You want to come visit me or something?
Well, like,
I'm kidding. So, you know, office hours are an important part of a college experience. You're either going to take advantage of them or you're not. It's weird, over my career, in the very beginning, I used to like have students in my office every day. Big groups, it would be, you know, having a good time, doing math problems. You know, and as time's gone on, that's kind of dropped off. I've seen less groups of students in there studying. And I understand people are busy, but if you have free time during my office hours, I would advise you come in. You can just sit down and do your homework, and if you have a question, you can ask me a question.
what are your office hours?
Well, they're in the syllabus, but I can tell you what they are. They're immediately after this class for an hour, and then today again from 2 o'clock to 3 o'clock. And then on Monday, Wednesday, I believe I have some office hours in there. I can put it in. I can just bring it up real quick. Let's see. Monday, Wednesday, 9:45 to 10:45, and then 1 to 2:30 on Monday, Wednesday. But on Tuesday, Thursday, again, it's immediately after this class until noon. And then from 2 to 3 today. And then on Fridays, we're on campus, but we have different commitments. You know, we are on committees and things like that, so I can never guarantee I'm free. So I say between 9 and 1 by appointment. Okay, so if you need to meet with me on Friday, we can do that. All right? I would prefer to meet with a student and do math than to go to a meeting. Okay, I can tell you that right now. So if you want to meet on Fridays, that's fine with me. All right? I just need to have, you know, someone request it, and that way I can talk to the chair and be like, yeah, bonus points if you come in on Friday and get me out of meetings. No. Yeah. Well, I mean, some meetings I won't be able to get out of, but others I you know. All right, so I think I'm ready. I don't want to get into any more of the details. This is what the orientation video is about. Make sure you cover that. Make sure you take that quiz. All right? I don't want there to be any issues here. Everyone clear on that? I need that quiz done by 1 o'clock on Thursday. I think it's just a yes or no. Is it one question? It's one question, yes or no? All right. Okay, that's it. We're going to get started here. All right, so I have the camera on this board, and I'm always going to have my screen on like this, and it's because of the way that the video comes out. I have to set everything up perfectly to not get glare. But during my lectures, I will also be bringing up my lecture notes, which are on Canvas, and you can go bring those to class and print them out if you'd like beforehand. But most of the time I'll project them here, and I'll make them a little bigger so you can see them. And Let's see. You tell me. Can you read that? You want to go a little bigger? Is that good?
Oh,
All right. All right, so we're about to start, but I wanted to do just a quick little recap of Cal 1 and then point out some of the things that you need to kind of know before we go and get into this, and then a little bit about what Cal 2 is going to be, all right? So for Cal 1, Cal 1 was essentially derivatives, right? Now this is my first class since the big summer break, which was like 4 or 5 weeks for me. So I need to remember how to write in English and spell properly here. I'm rusty, is what I'm saying. All right, I need to get going here. All right, so Cal 1 is differentiation, right? That's what it's about. And some of the topics that we covered in there, of course, the derivative. Okay, what else? And that was a big chunk, right? Chain rule is part of the derivative, right? So within the derivative, we have chain rule.
antiderivatives was also, and integrals was also.
Antiderivatives were towards the end. How many of you got to see antiderivatives in some respect? Okay, good. Limits. Okay, so limits, if we were going to put limits in here, this would have actually come in the beginning, right?
Yeah, because you can't have the derivative off the limit.
The derivative is a limit, so you have to define that first. Okay. Implicit differentiation, which is another type of derivative. That was a very special one.
It's
The-
part of derivatives, but
L'Hopital's rule. Ah. So let's see about that. It's spelled La Hospitals, but it's pronounced L'Hopital. So show of hands, who has not seen L'Hopital's rule? Okay? All right, that's going to be something you need to address, all right? I'm happy to meet with you to go over it. I also have on my videos for our class this semester, that'll take you to my YouTube channel. And on that YouTube channel, I have playlists for all these different classes. You could actually go find my Cal 1 playlist and bring up L'Hopital's rule if you need to.
Yeah, for
Okay.
some reason, Esquire didn't emphasize on hospital, hospital, just didn't like it, and didn't want us to use it.
Okay.
It's a very nice tool.
Yeah, I will.
You love it.
I won't comment. All right. So
Yeah.
L'Hopital's rule is an essential tool for computing limits, especially when we start doing improper integrals, which are antiderivatives, where we want where we're integrating to be like the entire number line, and we need to go to infinity or something like that. It just makes it a lot easier. And then even with sequences in series, which we'll get into chapter 8, it's just a great tool to have in the toolbox. So anyway, L'Hopital's rule, part of Cal 1. What else? Logarithmic differentiation. Arc that's Cal 2.
Mean value theorem.
Mean value theorem. Okay. What's that? Rolle's theorem, which was before the mean value. That's where we came up with mean value, or not, yes, mean value theorem is Rolle's theorem first. No one has mentioned related rates. I think you've all blocked it out of your minds, right? Word problems, you know, the volume of this is increasing at a rate of blah, blah, all those word problems. Implicit, you need implicit for that. How about optimization problems, curve sketching, right? All that? Okay. So the big thing that you're going to need, I mean, that's a lot of topics in Cal 1. Cal 2 is just as dense in material, if not more dense, than Cal 1. But the big things that you need, I mean, everything's important, but your derivatives and being able to apply the chain rule and take a derivative properly will help you tremendously in Cal 2, because what we're doing is we're reversing the process, going backwards. So if you understand how it works forward, it's going to be a little easier to understand the backwards process. But if the chain rule always caused you problems and you somehow got through Cal 1 without really understanding chain rule, then it's going to be very hard to undo that process. Understand? but we'll see how things go. All right. Geometrically in Cal 1, what we did was we basically took a curve and we picked a single point on that curve, let's say A, and what the derivative represented was the slope of the tangent line, right? Not the equation of tangent line, the actual slope. So if we take this tangent line, the derivative at A would represent the slope of that line, right? The slope of that line. That's what we did geometrically. And what we could use that for is to find highest and lowest points on curves, right? We could find the maximum and minimum values. We could do it on closed intervals. We could do it on open intervals, right? And there were different methods to do those two. For closed interval, it's called a closed interval method. And then for open intervals, you would just do some sort of like test points and figure out if your function is going up and then down or down and then up. So that was what we were doing geometrically. All right, so let's talk a little bit about Cal 2 and what it's going to entail. So for Cal 2, whoa. We're going to be doing the opposite of taking derivatives in here, which is called antiderivatives. And I know you were all, by show of hands, introduced to antiderivatives. You were probably shown the power rule, how to find the antiderivative of like x squared. You could probably find the antiderivative of cosine, things like that. But Cal 2, trust me, there's a lot more that's going to be involved when it comes to antiderivatives. And we'll take a big chunk of this first part of the course. In fact, it'll start not right away. It's going to start about, next Tuesday, and it will carry on all the way into March. Sometime around spring break, we will be doing antiderivatives. It's a big part of the course. And then once we get past the antiderivatives, we get into applications. So this is like, if you want to look at in terms of the course, we're going to spend about a third of the class figuring out how to find antiderivatives. Bunch of techniques that are involved with that. And then what we're going to do is applications. So now that we can actually take an antiderivative, what does it mean to have an antiderivative? What does it allow us to do? And geometrically for applications, what we're going to do is we're going to look at a curve, and we're going to be able to compute the area underneath that curve using the antiderivative. So it'll have a geometric meaning. Yeah, this is fine, but I don't like the way you'll be facing. What we might want to do next class is rotate these desks so that everyone's kind of looking sideways. Wherever you want. I just want you to be comfortable. All right, so we're going to find the area under a curve. All right. We're going to be able to find the area between curves. So if I have two different functions, we can find the area between them. And again, you might be like, well, big deal. Like, why do you need the area under a curve? Well, that's going to represent something. Just like the slope of the tangent line in Cal 1 could represent the speed of an object or velocity of an object at an instant in time, this area could represent, let's say, the total work done by a force over a period of time or something like that. So there are geometric connections that we can make to these areas. Then we'll do something kind of strange. We'll take this, let's say this region right here, and we'll wrap it around the x-axis. Like geometrically, just imagine wrapping that around the x-axis and coming up with some three-dimensional solid, which would be difficult for me to draw here, but I could try. Like imagine wrapping that around the x-axis. You might get something that looks like this. So like inside there, I could put my arm through it, through the center, because this thing has gone around the x-axis. So imagine my x-axis is coming in here, coming out here, that's my x-axis. So I've got this like three-dimensional solid. I can make this a little easier to see if I draw a more basic region. Like if I if I take this little rectangle and I wrap it around the x-axis, then it's going to look like this. That's pretty much it. It's three-dimensional.
Another line.
Pardon me?
Would you need another variable like X, Y, and Z?
Well, let's see. Yeah, I mean, because you're thinking we need volume, right? So it's going to maybe require 3 dimensions, so x, y, z. Turns out we don't. And we'll get to it, okay? But that's one of the geometric ideas that we're going to be doing, wrapping areas or regions around the x-axis and the y-axis. And arbitrary lines also, and just trying to figure out what the volumes of these things are, okay? So then there's more applications. I won't get into all of them. There's arc length, there's surface area, a bunch of different things. But that's going to be about another third of the semester right there. It's actually, it's a little less than a third, all right? But I'll just put a third. And then you get to series. Sequences and series, but I'm just going to put series. This is chapter 8, and that's a third of the course. And it's an important third, all right? When it comes to series, what we're getting into here is how we can use mathematics to approximate functions. So you have, let's say, the sine curve, right? The sine function. You type in, what's sine of 3 into your calculator, and you're in radian mode, and it spits out an answer. Like, how is your calculator getting that answer? Does it understand sine the way that we understand sine? We understand sine to be like a ratio of sides of a triangle, not necessarily, your calculator doesn't think that way. So in chapter 8, the buildup is to try and figure out, is there a way to take a function and approximate it with a series of functions? What Newton's method did was it gave us like a recursive formula to get to an answer. This one is similar, but you're just going to have to wait to see it.
So like, you're talking integration by parts, moving sums, and all that good stuff?
For series, what? What do you?
The calculator that makes a function.
Oh, yes. Okay, yeah. Anytime your calculator evaluates a function, you need to know how it's working. So how many computer science majors are there here? All right, so there's a couple. The series is important for understanding how calculators come up with these answers. And so it's a big section, or a big chunk of the course. It's chapter 8, and then we're supposed to get into chapter 9 also. Historically, I've had a very hard time getting to chapter 9. And I'm okay with not getting through all of chapter 9 because it's stuff that I think can be picked up pretty easily. Sequences and series, on the other hand, you have to spend a significant amount of time on. It's not just, oh, okay, there's a formula, now just apply it. There's a lot of thinking that has to go into it. All right, so that's pretty much Cal 2. Now, what are some of the things you need to know? All right, so like pre-cal, you need to know everything. No, I'm just kidding. You need to know all the basic trig functions, what the common angles are. If I say what's cosine of pi over 3, you need to know that. It's not something you're pulling your calculator out and putting down, so it needs to be something that's automatic at this point. You need to know all the basic important identities, Pythagorean identities, sum to difference, or sum and difference identities, your double angle identities, all the ones that always came up and keep appearing. Here's one this is one that everyone should know, that this is equal to, how do you make that instead of 2x, just the argument x instead? It's 2 sine x cosine x. Okay, that should be automatic. If it's not, it's okay. I'm not saying, okay, go drop the class, but I'm just saying that's the expectation, is that this is not, when I put that up there, you're like, oh yeah, like I've seen that, yes, okay, got that. Not like, oh, what is he talking about? Okay, so there's important things that'll come up that I'm not going to spend 30 minutes reminding you, about. So just be aware. And I'll point it out when I'm talking about it. I'll be like, if you don't know this, go back. I'll put a star next to it. Go back and look at this. Calculus, again, I told you in Cal 1 you need to know the chain rule, right? And then everything else, but the chain rule is the big one. All right, well, let's have a different conversation. I don't want to kill an hour of class here, but I think we need to have a conversation about, why is Calculus 2 important? Why is this a requirement for your degree? And, what's the value of this course? What's the point? Because you're not going to be finding antiderivatives in your career field, right? Most likely, if you have to do an antiderivative, you're going to go to Wolfram Alpha, or you're going to go to some engineering program that you're using, and you're going to find an antiderivative there, and you're going to trust the answer, and you're going to make decisions based upon that answer, right? So why go through all of this formal education when the computer can do most of it, or we've moved past, we're beyond that,
What happens when the computer goes down?
If the computer goes down, that could be an issue, right? They'll just go buy another one. Your company's got money. Just go buy a new computer, right?
Well, what if you don't work for a company? You still
Yeah.
need to
What if
interpret
you're-
the information.
Yeah. You still need to what?
Interpret the information that the computer is giving you.
Yeah, for people who are computer science majors especially, you have to know, the algorithms that you're creating. You have to know how they work, and to know that they're going to give you good theoretical, solid answers, you have to understand the theory, what's going on.
Realistically, you have a lot of companies will say, we've got a big project, we're forging new ground.
Mhm.
We need to be able to contribute. If there isn't any already existing software, because you're making the next Tesla car, or the next space rocket, or something like that.
Yeah.
Or a lot of companies have big hybrid teams of engineers, chemists, geologists, all these people from different backgrounds working on one project.
Yeah.
And Calculus 2, or math, is that language that connects everyone. So you may be a specialist in your field and me in mine, but we have enough of a common language that we could work together to complete the project.
I think you're on to what I'm thinking, and it's time for me to update my virus. If you're working for a company, my brother works for a very large and powerful electrical engineering company in Austin, and we talk a lot about the people that he works with. And one thing that they all have in common, no matter what their degrees were in, is they're all problem solvers. And that's what this course, that's what Cal 1 is about. It's not about can you take derivatives, can you integrate. It's problem solving and how you address learning, and when you're faced with a challenge, whether or not you just kind of wither or if you actually go after it. And that's what we're trying to create here. Independent learners that are motivated, can think critically, can solve problems. That's what you want. That's why this is in the degree plan. This is another course that requires those sorts of skills. So that's, to me, the main theme. And so don't get caught up in when will I ever use this. And well, it's the parts of the brain that you have to use to do this that are important. All right? Now, I do also understand there's some people in here who are like biology majors, and this is like the last math requirement, and maybe that's not going to, that kind of model doesn't work with you. But all I can say to that is, well, they're just, they're weeding out the herd. There are too many people who want to be doctors, so they just up the math requirement, and that weeds out a lot of people, right? And that's the truth. When I first started teaching, pre-cal was the requirement for pre-med. And then I went up to Cal 1, now it's up to Cal 2 for a lot of major institutions, so that's just the way it is. Okay, any comments or concerns before we start? You all ready? All right. I thought of a policy. I just want to just bounce it off you real quick. I was thinking about, how do I help students that are struggling? Taco Tuesdays. And one of the problems I always have is that, after the first test, I'll have students that don't do so well, and then they come in the next test, they don't do so well, and by the end of the semester they're not passing and they have to drop or whatever. And I never have an opportunity to sit down and talk with them. So what do y'all think of this policy? If you do not pass the first test, 70 or anything below 70, you have to come in, sit in my office, and we have to have a sit-down meeting, like a 20-minute, little 15, 20-minute, like,
Like a come
let's,
Jesus meeting?
I can't say that, but just some sort of, I want to be able to get to the issues, because a lot of times students will come to me like the week before the finals and be like, you know, man, I don't think I'm going to pass, and then they tell me their whole story about how they, you know, I don't know, just all these different stories, right? And at that point, it's too late, you know, and there's not much I can do. So I'm thinking of trying to intervene earlier, but I can't force you to come to my office. So I'm going to have to figure it out. Does anyone have like a problem with that? Does anyone just instinctively be like, no, if I fail, I'm going to fail, and I'm not going to have to go talk to anyone?
No, that's a good.
You seem-
This class doesn't get
If it's a first test, I mean,
That's right.
fair game. I mean,
Yeah. Okay, we'll see. I'll do something, all right? Maybe even a phone call so we can just talk, whatever it is. Yes, in this class, it was just mentioned by, what's your name? Jonathan. Okay, I'm not good with names, but I'll do my best. This class does not get any easier as it goes on. You know, it's a steady applied force the entire time. There's certain parts where it's even harder force. So it's a marathon, right? This course is a marathon that you have to sprint through, all right? Here's a sign-in sheet. Please find your name, and in the column for today, which is 17, just initial. I know it's a very small little square. Just put a little initial in there, and then pass that around. That's my attendance. All right, we are going to start. Let's see how much time I ate up. 30 minutes, not bad. All right, so we have a little over an hour. We're going to start in Chapter 3, Section 5 out of the book. And the title of this section is Inverse Trigonometric Functions. Now, inverse trigonometric functions is something that you covered in pre-cal. And we're not interested in rehashing that entire topic in pre-cal. But what we do want is to talk about the derivatives of inverse trig functions. So if you go back to Cal 1 and you think about in Cal 1, you should already know the derivative of sine, cosine, tangent, secant, cosecant, cotangent. There are 6 trig functions, right? The standard trig functions. You should know what the graphs of these look like. If they have domain issues, you should know their domain restrictions. And then you should know what the derivatives of all of these are, right? And if you don't know, you should at least have the formula sheet that I provide to you on Canvas that you're supposed to print out and bring to class, and that formula sheet includes those derivatives. But you should at least know derivatives of sine, cosine, and tangent off the top of your head, right? So this section is about, all right, well, let's go back a little further to pre-cal. Let's talk about the inverse trig functions, because we never in Cal 1 talked about their derivatives. We never did. So wonder if they have derivatives. It turns out they do, and we want to know what they are. So you know what? You can probably sit right here. Yeah, right here. I'm not going to force you to, but you could face, yeah, you could, okay? However you're comfortable right here. So we want to know what the derivatives of the inverse trig functions are. So this section begins by just reminding us of what they are. And that's what these notes, when I have these notes up here and I'm scrolling through these, I don't expect you to write this all down, because that's why I provide them for you, okay? Remember what it means to be a one-to-one function? Where's the ruler? You know what? There it is. All right. This is my ruler, pointer, / encouragement stick. All right? Okay.
Rep on the knuckles didn't do anything.
All right, so what does it mean for a function to be one-to-one? Well, that meant that for every input, there's exactly one output. So you can never have something get plugged into a function and have it go to 2 places. Then it wouldn't be a function. But you can never have, on the range side, you can never have the output come from 2 inputs. So it would look like this. Every input goes to exactly one output, and every output comes from exactly one input. So you could not have this happen. That would not be one-to-one. So there's a one-to-one correspondence. Now, why is one-to-one? Why is the property of one-to-one functions important? Well, you need that in order to have inverse. You can't have an inverse without the one-to-one property. So one of the simple tests that we use to figure out whether or not a function was a function and whether or not it had an inverse was the vertical and horizontal line tests. Does that ring a bell? So if I draw a function, or if I draw a graph, let's say a circle, is that a function? No, because it fails the vertical line test. So once it fails to be a function, you don't even have to worry about the inverse part. How about something like this? Like a parabola. Is that a function? Yes, because it passes the vertical line test. The vertical line never hits it more than once, right? Is it one-to-one? No, because if I draw a horizontal line, I hit twice, and that means that you have the same output coming from two different inputs, and that's not one-to-one. All right, so we need it to be passing both the vertical and horizontal line test.
So in order for it to have an inverse, it's gotta be either constantly increasing or constantly decreasing.
Constantly increasing or decreasing? That's a good question. Does it always have to be going up or down?
Because like if it stops, like obviously if there's holes and things like that, like it doesn't really matter.
If it has jumps, you can still have jumps and it still have an inverse, but you'd have some domain restrictions. So like you could have like something like that. That would still pass the vertical and horizontal. And you could come up with an inverse, but your inverse would look just as weird. It'd have jumps and breaks also. All right, so if we go back and we look at our trig functions, okay, now I'm looking at the 6 trig functions from pre-cal. The sine function, of course, is a function, right? But is it one-to-one? No. So it doesn't have an inverse, right?
Well, only if you have domain restrictions.
Yeah, we would have to cut it off in order to work. But just in general, it doesn't. Same with cosine. That fails to have an inverse because it's not going to pass the horizontal line test. The tangent function. Well, if you look at just this piece, that would be one-to-one, but the fact is it's periodic. So since it repeats itself, it would fail the horizontal line test also,
Unless you have, again, domain.
unless you restrict the domain. And cosecant, which looks like this, which I hope you remember, is just basically taking the sine curve and at all the peaks and valleys, drawing these little parabolas that are bounded between these two vertical asymptotes. But that's your cosecant function, and it is not invertible either, because invertible meaning you can't find its inverse, because it fails the horizontal line test, unless we restrict, and so on and so forth for the other two. We've got secant x, can't do it, and cotangent, same thing. All right, so we got some issues. So what we need to do is restrict them. Okay, this is a recap of pre-cal. This is not supposed to be new information, but what we did to get around this is that we restricted the sine function. So let's deal with just the sine function first. So how about this one? If I take the sine function by itself, it has no inverse, just like this. But what about if I restrict it to just that piece right there?
Yeah.
That would have an inverse. It would pass the vertical and horizontal line test. And very important here is that in order to say that this would have an inverse, notice that the range of the section that I cut off, the range goes from -1 to +1, right? So you get the entire range in that region. You need that because if you try and cut it off, let's say we just did that piece, just right here, yes, that would have an inverse, but you would not get all the outputs that you need. You need the entire range to be included, -1 to 1. So that would work, yes? But that's not the only thing I could have taken. I could have taken another piece of the sine curve over here, right? There's the sine curve. I could have taken this piece, and that would have an inverse, right? And there's an infinite number of these I could have taken, right? So which one do we take? Well, we all had to agree, all right? We, meaning humans, had to agree. Doesn't happen very often, but we did. We actually agreed. And we all said, that's the piece right here, this part in blue. And I'm going to take the sine curve out. We all said, look, since there's an infinite number of intervals, we could have chopped it off. What we're going to do is we're going to take between negative pi over 2 and pi over 2, look at the sine curve just between there. It will go from negative 1 to 1 in that interval, and that covers the entire range of the sine function, so it will have an inverse in there and it will cover that entire range. So we're good to go. And that's the standard domain restriction for the sine curve. All right? Yes? Does that ring a bell? Negative pi over 2 to pi over 2? All right. And then we had to do the same thing for cosine. But before that, let's get some notation out of the way. Here's the notation we use. You'll see arc sine or sine with the negative 1 up there. I usually use this one. All right? As long as we agree that we're going to restrict our domain between negative pi over 2 and pi over 2. Then it's 1 to 1 and we have an inverse. And we have this important property that when we say arc sine of x equals y, what we mean is that sine of y equals x. So the input here is the output of the sine function. The output here is the input of the sine function. So it's the domain and range switch places. All right. So if you graph the two together, if you graph both the, man, that's really big. Let me see if I can zoom this out a little bit. If you graph the two together, then what you'll notice is that they are reflections of each other over the identity. So if you take the diagonal, which is f of x equals x, and you reflect the blue one over that identity, you will get the red one, right? And that's every inverse has that property. They're reflections over the identity. So those are the graphs. And now we're just going to do some examples. All right, so let's take a look at these here. All right, so find arc sine of 1. So what is this really saying to us? It wants to know the angle, right?
Yeah.
It wants to know an angle. What angle do you plug into sine? So sine of what angle? I'm going to put a question mark here. Will you get 1? Right? That's what it wants to know. Excuse me. Pi over 2. All right, so this is where your background comes into play, like how comfortable are you with these things. I go off the unit circle. That's my big go-to when it comes to trig functions. I always go to the unit circle. Not always, but most of the time. All right, so when you're on the unit circle, the x and y coordinates are related to the angles that you're at. So if I'm looking at some arbitrary angle, theta, then this x and y coordinate are related by the following. The x coordinate is always cosine of the angle, and the y coordinate is always sine of the angle, right? So if we're saying sine of what angle is 1, we're really saying to ourselves, on the unit circle, where's your y coordinate? 1, right? And that's going to happen up here, because that's the point 0, 1. And so what is the angle that would give you that y coordinate of 1? Pi over 2. And we're going to stick to radians, but we should also be comfortable knowing that that's 90 degrees. So the answer here would be pi over 2. Good? All right. How about this one? Arc sine of root 3 over 2. So I used two different notations here, right? But they're both asking the same question. It's just the two different notations, except I'm plugging in 3 pi over 2. So I'm saying where sine of what angle is root 3 over 2. So you go to your unit circle again, and you say, where is my y coordinate, root 3 over 2? That's going to happen right here at this angle right here, because that was what, 1/2 root 3 over 2? That's not the only place it happens, though. It also happens here, negative 1/2 and root 3 over 2. Doesn't it? But there's a domain restriction, right? Your domain restriction is that you must be between where and where? Negative pi over 2 and pi over 2. So let's take a look at where those are. Okay, here's 0, right? 0 degrees. Negative pi over 2 is straight down, and pi over 2 is straight up. So you're only allowed to be between here and here. Your answers, right? Your answers to any inverse sign have to be between negative pi over 2 and pi over 2. And so this region over here is completely not allowed. We just ignore it. So I don't care about any answers over here. So the only answer it could be would be this one, which is the angle pi over 3 or 60 degrees. Okay? I'm going to make one up here, all right? How about cosine? No, cosine's too boring. Let's do arc sine again. Let's do arc sine. Let's change it to negative 1/2. Arc sine of negative 1/2. Okay, so you're saying to yourself, where on the unit circle is my y-coordinate, right? Negative 1/2. It's going to be here, right? Or here. Because this is root 3 over 2, negative 1/2. And this one over here is negative root 3 over 2, negative 1/2. But I can throw this side out completely. I'm not even worried about that. Right? So the reason why do you think I put this example up? I've already heard the right answer. I've heard a couple of people.
We were looking for some.
That's right, because some people are going to say 11 pi over 6. That's incorrect. Yes, because to get, I agree that 11 pi over 6 is coterminal. It's equivalent, basically. But in terms of an actual value, the domain restriction says that my answer has to be between negative pi over 2 and positive pi over 2. And if you say 11 pi over 6, you've gone past pi over 2. You're a positive number, right? A positive angle to 11 pi over 6, and that's outside of this interval. So instead, what you have to do is you have to go backwards by pi over 6. So negative pi over 6 would live inside of this. So the correct answer here is negative pi over 6. Got it? Everyone clear on that? Any questions? Okay. All right, let's move on. Okay, if we want to do the same thing for cosine, we're going to have to restrict the domain, aren't we? And so we have similar notation. We can use this cosine inverse and blah, blah, blah. But what's the restriction? What's the domain restriction for cosine? 0 to pi. 0 to pi, all right? So I'm not going to go through and draw pictures again or show you pictures for all of these. Just remember that for cosine inverse to exist, we have to restrict the cosine function between 0 and pi. And so that's like this. Here's cosine. Goes both directions. And we cut it off here, and we go to pi right there. And we just take this section right there, and we cut everything else off. So that's a different domain restriction, isn't it? And in terms of unit circle, that means that your answers can only come from the first two quadrants between 0 and pi, but nothing in the third or fourth quadrants. What about arc tangent, inverse tangent? What's the domain restriction? Negative pi over 2 to pi over 2. It's the same thing as the sine. Okay? All right, and then the other three are in the book, and they're not going to come up very often, all right? But just be aware that there are domain restrictions there. Now, there is an important property with inverse functions that we like, that's very useful to us, and it's called the cancellation property. We know that inverse functions kind of undo functions. So it's kind of like I always talk about functions in my college algebra classes like a car wash. You know, you put a car in one end of the car wash, it comes out the other side clean. The inverse function would undo that, right? So it's like it would basically throw all the dirt back on the car and take it and send it out the other side dirty again, right? So that's what inverse functions do. They undo whatever the function did. And so we have these properties that if you have sine and you compose it, that means you're putting arc sine, this function, into the sine function, then they just wipe each other out and you just get x. And it works the other way around. If you do arc sine of x, you just get x. But there are some things you have to consider. There are some tricky things that can happen. And so I'd like to show you an example of something that would be tricky. All right? I actually don't do it here, but I'm going to just throw it on the board. All right, so let's try this. The domain and range switch, yeah. Let's do this. How about this one? What's sine of arc sine of -1/2? Your instinct is going to tell you -1/2, right? Because that's the cancellation property right here. Yes? Okay, so let's check it. Let's just check it. Did we just do this problem?
Yeah.
Okay, what did we get? -π/6. Okay, so this is sine. This was -π/6. And what is sine of -π/6? Nope, sine of -π/6. So we just did this problem, right? Just a second ago? We just did that?
Well, we did -π/3. Just a second ago, that's what we did.
Oh, it's -1/2.
No.
We just did this problem right before this, didn't we?
Yeah.
And we got -π/6 as our answer. Now, what I want to do is take sine of -π/6, which means give me the y coordinate on the unit circle at -π/6, which is -1/2, right? So it is this property, isn't it? This worked. This worked.
It won't work all the time, though.
Because it's within domain. Okay? So that worked. No trouble. But we don't want to get into a habit of just seeing the two together and always just dropping them. Let's show you one that may not work. So how about this one? How about sine inverse of sine of, let's go 7π/6.
You use the terminal angle in the right part of the answer.
Mm-hmm. Yeah, let's just see what happens though. If we get ahead of ourselves and we're like not thinking, we'll just go, oh, it's this, and my answer should just be 7π/6. But this x is not inside of here, is it? Yes.
Could you possibly use it?
Yes, that's what we're going to do. But I'm even going to do it a little easier than that. Okay, watch. I'm just going to go here and do it piece by piece. Look, 7π/6 is right here, isn't it? Okay. What is sine of that angle? It's the y coordinate, isn't it? So the y coordinate here is -1/2. So this inside piece is -1/2, right? That inside piece is -1/2. So now what I have is this, arc sine of -1/2. Right, that's what that really is. And what is arc sine of -1/2? We just did this, right? We just did this, not the one right before, but the one before that. And the answer to that was -π/6. So you see, it's not just spitting out 7π/6. That's where that cancellation property gets tricky, is that you must be within the domain for this property to work. If it's not within the domain, then you can still get answers, but you just have to be careful. Any questions on that? We're good? Yeah? Same with cosine. Yep. Now the tangent's a little different. Tangent's pretty safe, and it's because it's when you look at the graph, the domain, the range is all real numbers, so it works out a lot nicer. Okay. Let's go. Keep going. Now, that's all just kind of like let's recall pre-cal. This is stuff we did in pre-cal. But now we get into the derivatives. So what are the derivatives of these inverse trig functions? What are they? So here's some things we're going to need in order to find the derivative. What I'm going to do is I'm actually going to prove to you what the derivative of arc sine is. And after I do that, I'm just going to tell you what the derivatives of the other ones are, because those could be found using the same method. So you're not going to have to prove to me on a test, like derive how you get the derivative of arcsine. But I want to show you at least once where it comes from, instead of just saying, oh, here's the formula, all right? But to do this, there's a couple things that you need to know. You need to remember reference triangles and implicit differentiation. So reference triangles is something that you did in pre-cal, and implicit differentiation is something you did in Cal 1. And if you don't remember, you'll see as I go through this first example how it's all going to work. All right, so that's my goal right there. If y is arcsine of x, find the derivative. So y is equal to arcsine of x, find y prime. Now, if you look in the book or you look on your formula sheets, let me tell you what the answer should be, all right? The answer should be y prime is 1 over the square root. What page is this? On your reference pages that I put on Canvas, it's reference page 5? Yeah, okay, it's number 19, the formula 19. 1 minus x squared. All right, that's the answer. But how do we get to that answer? Right, that's what I'm going to try and show you. Understand? All right, so how do we do it? Well, we can't just take the derivative of both sides, right? If I take derivative of y with respect to x, the answer, this would be y prime, wouldn't it? Yeah. But then what's derivative of arcsine of x? That's the whole point. That's what we want to know, right? So we can't take the derivative of the right side at all. So what we will use is what we do know about the arcsine function, and that it's the inverse of sine. So I'm going to bring sine into this now. So what I'm going to do is I'm going to take sine, bless you, take sine at both sides of the equation. Now, I said I'm taking sine at both sides of the equation. I'm actually not taking sine at both sides. Yes, but even then it's not really applying. It's using a property that the function is 1 to 1. See, when functions are 1 to 1, we have this property. It says f of x equals f of y if and only if x equals y. That's a property of 1-to-1 functions. It means that, look, you can read this both ways. If the function is equal to each other, right, if f of x is equal to f of y, that means that this x and this y had to be the same. It also says that if x and y are the same, then if you evaluate the function at both the x and the y, then you have to get the same value. All right?
Two F's on
If and only if.
Oh, okay.
That's what this IFF means. It works both ways. So it's this means this, and this means this. You can also use a double implication arrow like this, if you don't want to use that notation. But the point is that not all functions behave like this. I can give you an example of one that doesn't. If I define f of x to be x squared, okay? Then somebody give me, oh no, I'm not. How about this? Do you agree that f of negative 2 equals f of 2? Do you agree with that?
Yes.
If I square negative 2, I get 4. If I square 2, I get 4, right? That's true. But does that mean that these two were the same?
No.
Right? But negative 2 does not equal 2. Right? So this is not a 1-to-1 function, though. If it's 1-to-1, then this has to be true both ways. So when we look at this right here, what I want you to see is that because arcsine is a 1-to-1 function and sine is 1-to-1 because we've restricted the domains, that if I take this to be, just imagine this and this right here as being like the, I know it's going to look weird, but this is kind of like the x equals y. And then this right here is sine of x equals sine of y. See this junk in here and this junk in here, that the equality has to be the same. I'm just pointing that out because I will say, and you'll hear a lot of instructors say, we're just going to take sine on both sides of the equation. It's not really what we're doing. We're taking advantage of the one-to-oneness of the functions. But because we don't want to get all bogged down with all this, we just say that, all right? If that confused you, don't worry about it. I mean, I think you'll be okay. All right, so there I am, right? Now, on the right-hand side, something happens. I get the cancellation property, don't I? So long as x is in the proper restricted domain, all right? Which I'm going to assume it is, because then this wouldn't have been defined to begin with. So within the proper domain restrictions, we have this. Now, why in the world would I have done that? I mean, what's the advantage here? What have I done that's going to cause... Yeah.
You're going to implicitly take...
I know the derivative of sine, right? I didn't know the derivative of arc sine, but I do know the derivative of sine. So now I'm going to use implicit differentiation and take the derivative with respect to x on both sides of the equation. With respect to x. So notation-wise, what I'm doing here is I'm taking the derivative with respect to x on the left side and the derivative with respect to x on the right side. So I'm taking derivative on both sides with respect to x. And do the right side first, because I think it's easier. What's the derivative of x with respect to x? 1. So the right side is 1. The left side is tricky. Not tricky, but you got to remember something. So what's derivative of sine of something? Cosine of that something, whatever that something was, right? Cosine of that something. Times, now you have chain rule, which means you have to go inside to the argument of the function, which was y, and take the derivative of the y with respect to x, which is y prime. I'm just going to write y prime. You could write also dy dx, depending on your Cal 1 instructor. They may have stressed one over the other. But y prime for us is equivalent to dy dx. It's just two different notations that mean the same thing. Any questions? Okay, so look, we've got y prime, right? That's a good thing. So let's solve for y prime. Let's just get y prime by itself. So I put, how about divide both sides by cosine y? That good? So far, this is, I mean, it looks like we've got an answer, right? The problem is that our answer has y in it. I'd prefer that it have x. Because my original function, right, my original function, y equals sine of x, was a function of x. Therefore, its derivative, I want the derivative to be a function of x, not a function of y. Right? So let's try and figure out if we can convert this to an x somehow. So this is where you need the reference triangle. All right? This is where you're going to need a reference triangle. So where do we go to get our triangle? Right here. I want you to look at this right here. I put it in red because it's important. That's what you got after we did the application of sine on both sides, right? We got this equation right here. This is a relationship between x and y, isn't it? And what I need to do is convert an expression in y over to an expression in x, which means I need a relationship between the two of them, and there's one right there, all right? So I'm going to grab that, and I'm going to draw a right triangle from this picture. And you're like, what? Draw a right triangle? What are you talking about? Well, I'm going to use y as my angle in my right triangle. And what is, by definition, sine of y? When you look at right triangles, it's opposite over hypotenuse, right? So the ratio of the opposite side divided by the hypotenuse side needs to be x, doesn't it? But x, I could look as a ratio if I put it as x over 1. Isn't that a ratio? No. That means if I label my hypotenuse x, hypotenuse, my opposite side x and my hypotenuse 1, then sine would be this over this, which is x, isn't it? And that's this. So do you see that that triangle matches that equation? Yeah? So what's the advantage of that? Well, we want to know what cosine of y is, right? Cosine of y is the adjacent side divided by the hypotenuse. But you don't know the adjacent side. Not right away. But you know that this is a right triangle. You have 2 of 3 sides, so you can always solve for that third side, can't you? So I'm going to label this side here. Let's label it A for adjacent. I want to know what A is. So we can write it out, right? sorry, I'm kind of all over the place here. I know that a squared plus x squared must equal 1 squared by the Pythagorean. And that means a squared is 1 minus x squared, just subtracting x squared on both sides. Square root both sides. And when you square root both sides, you get a is root 1 minus x squared. Now, technically, we're supposed to have plus or minus,
Because we initiated it.
because we came in there with the square root. But a is representing the length of the side of a triangle, and so it's not going to be negative, so we're going to go with the positive. Yeah? So this side right here is really square root of 1 minus x squared, right? And so with that, if I ask you now, what is cosine of y, you're going to say this over this, right? Adjacent over 1. And now I'm going to come back here, and I'm going to write 1 over, and then square root of 1 minus x squared over 1 is just square root of 1 minus x squared, right? And that's what I told you it was, right? So we've proven where it came from. Now I said you're not going to have to do this on a test. I'm not going to ask you to derive the derivative of sine or cosine. But you will have to use reference triangles and you will have to use implicit differentiation in this class. So this is a good exercise just to kind of get you thinking about those things again. All right, how are y'all feeling? You okay? Okay. So we did that one. I believe in the textbook, in some of the exercises, and I want to say it's a homework problem. I believe for homework, you have to prove that the derivative of cosecant inverse of x is negative 1 over x times the square root of x squared minus 1. So you do have one of these for homework, but I don't see myself giving you one of these on a test. That's what I said. So that'll be a fun exercise. And like I said, that exercise will be worked out and it'll be on homework, my homework solution videos online. Now, about my homework solution videos, what I recommend you do, all right, for those, is start doing your homework, have the computer on, have my videos there, and start working through the problem. And then when you get to a point where you're like, yeah, you know, I've put in a couple of minutes of work here, I feel pretty good, play my video out, see if we're on the same page, and then work to a point where you get stuck, and then continue, you know, pause my video and then continue. If you just sit there and watch my videos, you know, with popcorn and a beverage, then if you just watch me do problems, that's not going to help you at all, you know. So, all right. Now that we know what the derivative of arcsine is, all right, we have a formula for it. We know that the derivative of arcsine of x, I'll use that notation, is 1 over square root of 1 minus x squared. Because we have that formula now, we can theoretically take the derivative of arcsine of anything, but incorporate also product rule, chain rule, quotient rule. All the rules that we had in Cal 1, we just have a new function now that we can differentiate. So here's an example. Find the derivative with respect to x of this. I'm going to give you 2 minutes to see if you can do that on your own, then I'll go through it. I'll give you a hint. It's chain rule, okay? You've got that. So we'll just see what you can do. I'm not going to quiz you on it. So it's arcsine of something. It's up here. I don't know if you can see it. Oh. Oh. Okay. Yes.
Is that right?
Mm-hmm. Yep. That's it. Yep. Mhm.
1 over 2 root x, right? Yeah, I got that part. I'm talking about, then you have to do that. Yeah, it's the derivative of that is, yeah, 2x over 2. But it's changing, you gotta do that one first, the square root. Well, yeah, I know.
All right, I'm going to work through this one. And if you got it at the end and it matches my answer, you can pat yourself on the back. Missing a parentheses. All right, so when we look at this, we have functional composition. We have an outer function here, which is the inverse sine function. Inside of that, we have a square root function. And inside of that, we have a polynomial x squared plus 1. So there's kind of like 3 levels or 3 layers to this onion, and that means we're going to do chain rule when we differentiate, starting with the inner, outer, outside, starting with the outside. So imagine here that you have arc sine of this red big blob right here, right?
Arc sine of that jump.
The derivative of that, right? Arc sine of this junk, which is what I like to call it in Calculus 1. This arc sine of some junk is going to be, according to this formula, 1 over the square root of 1 minus. So I'm just copying this formula down, right? But instead of having x, I actually have what instead of x right here?
Put that jump.
That big red junk right there, which is the square root of x squared plus 1, but that quantity squared.
Times.
Then we go inside, we've taken the derivative of the outer function arc sine.
So it's 1 over.
So I'm going to go inside and take derivative of the square root of something, right? That's what I've got next.
I forgot 2.
All right, so I'm going to say times 1 over 2 root x. So this again is going to go back to your Cal 1 class. How comfortable are you with taking the derivative of the square root of x? Now, all my Cal 1 students, I could give you a pop quiz right now and you get 100 on it, right?
Yeah.
So let's not do that.
Let's do that.
Instead, let's hear at least my old Cal 1 students. What's the derivative of root x? 1 over 2 root x. That's it. 1 over 2 root x. And for those of you who didn't have me for Cal 1, you just need to remember it that way because it happens so much. We take derivative of root x all the time. And so you should just know this by formula. I agree that this is also 1/2 x to the negative 1/2. I agree with that, all right? I'm not saying it's not that, but this is just an easier way to remember it. It's always going to be 1 over 2 square root of whatever was in here. So that means out here I'm going to put 1 over 2 root x? No, root of whatever was in the root, right? And the argument in here was, we could actually call that the radicand, is the x squared plus 1. Any questions with that? So now we've taken care of the root part, and we work inside again to the last layer, and we multiply now times the derivative of what's in there, and hopefully everyone, derivative of x squared plus 1 is just 2x. And that's it. Now I'm going to clean it up a little bit. I notice I can cancel 2's. I can actually square the square root here, right? And the root will go away. So I've got something like this. 1 over square root of 1 minus. Now what do I do here? I replace. This is just x squared plus 1, right? But the minus has to distribute because that's, right? So you've got to have like that. And then over here, this is just x over root x squared plus 1. And when we distribute through here, what are we going to get?
Negative x squared.
Negative x squared under there, right? So we have 1 over the square root of negative x squared times x over x squared plus 1. And at this point, we would kind of be done, but you should be asking yourself, you should be like scratching your head right now. Why?
Should be something that you should clean up.
Yeah, but there's something in here that should be worrying you. That negative under the radical like that. You know that x squared is always positive, right?
Yeah.
Then if you make a negative out of it, you're going to have a negative for short, and you're going to have a root of a negative, which means imaginary number, right? Which isn't going to happen.
Not here anyway.
Not here. And there's two reasons why I put this problem in here. One is because I do want to talk about imaginary numbers quickly, and I also want to point something out. All right, but first let's talk about the fact that we can't evaluate this. Now, the square root of negative x squared is not defined in this class because the calculus that we study, okay, this entire book, and every calculus 1, 2, and 3 class that you could take, that you would take at a university, is known as calculus of one real variable, or multivariable calculus, but the variables are real numbers. We're not allowed to use complex numbers in here. All right? We stay away from them. We avoid them on purpose. And it isn't until you get into a class called complex variables. Make sense? Complex variables. Now your variables are allowed to be complex numbers. And that's an entire different class. That's when you actually start to allow this to happen. You start dealing with it. And it becomes complicated, to say the least. But here, this is not defined. So there are 2 points I'm trying to make. This isn't defined. You should recognize that and just know that in calculus, this is not going to happen. I did this intentionally. Yes?
Sorry, is the radical supposed to still be there?
Yes. Yeah, sorry. I was getting ahead of myself. Thank you for pointing that out, though. So the 2 points were, I did this because I want to talk about complex numbers, that we don't use them here. All right, so this problem basically makes no sense, and I should not put something like this on the test. And the other point I want to make is we could have known this from the very beginning. We could have realized this kind of from the beginning. And let me just write down what the original... Okay. Look at the original function that I was asking you to take derivative of. Look at the radicand, x squared plus 1. X squared plus 1. If we look at just x squared plus 1, even if I just graph it, it might even be easier for you to see this. Isn't that a parabola that's up here at 1? Yeah? So the smallest that this could ever be under here would be 1. Other than that, right, it would be bigger than 1. And if I take the square root of a number that's bigger than 1, it's still bigger than 1. And if you try arc sine of something bigger than 1, what's wrong? It's outside the domain restrictions. So this function actually isn't even defined for any values of x except 0.
So it's her question.
Well, no, again, it was me pointing out 2 things. This function doesn't make any sense except at one value, and that's 0. Does everyone see that? If I plug in 0, I would get 0 here, 1, root 1 is 1, arc sine of 1, we have an answer for. But everywhere else, this function doesn't exist. Understand? Which means the derivative should be crazy. Something should tell us there's something crazy going on here, right? And it's nice that mathematically it does tell us there's something crazy going on here, right? There's problems. This is pointing it out to us. There's problems. So could you maybe define this function for complex numbers? And the answer is yes, you could. And then this derivative would make more sense. But we don't get to study that here. That's kind of like more for my math majors. Do I have any math majors? Okay, so that's later down the road. Realize right now that we're still in a, I like to call it like a fish bowl. We're still in the fish bowl, all right? Here's your fish bowl. That's a fish. So the real numbers, we're still in here. But later on, there's a bigger universe of numbers that we use, and it's just not time yet. It's just not time. All right. 20 minutes. We got 20 more minutes. See what we can do. Look, I'm going to always try and go to the end of class. I'm not going to cut out early unless it just doesn't make sense.
This would be a D&E, does not exist. Kind of.
Not a D&E, that would just be a dumb problem for me to give you. But the method, as far as what we did for chain rule, it was all right, you know, and that was important to understand how we applied the chain rule. But I'm trying to make a point out of that problem with why the answer just came out weird. All right, so there are derivatives of all the inverse trig functions. We could derive all of them. You're asked to derive one in your homework, but I'm not going to go through all of them, all right? I'm not going to sit here and derive them all, and I'm not going to put them all up on the board. They're in your book. They're also on your formula sheet, all right? So one of them, though, is going to come up a lot, and you need to recognize it. It's got to be one of those pattern recognition things. And that's the derivative of the arctangent. So I'll put it up here for you. The derivative of arctangent of x is 1 over 1 plus x squared. And you could also switch that around. You could put the x squared before the 1. You could say x squared plus 1. It doesn't matter. That's the derivative of arctangent. So with that said, I'm going to quickly derive this function. We have y equals the square root of natural log of arctangent of x. So again, we've got chain rule. We've got 3 layers to it. The outer layer is the square root. The next layer in is the natural log. The next layer in is the arctangent. So let's do it. What would the derivative of this be? So first it's root, right? Root of something. So 1 over 2, root of all that stuff. So 1 over 2, root of natural log of inverse tangent of x. Okay, that's just the chain rule on the outer layer. Just the root. So chain rule says now times, multiply that by the derivative of what's inside, so forget that part, we've done the root. So natural log.
So 1 over...
The derivative of natural log of x,
1 over that,
or natural log of something, is 1 over
that jump.
that something. What's the something?
And the tangent
Arctangent of x.
times the derivative. What's in it?
That takes care of the natural log. And now we go inside of that and take derivative and tack it on with multiplication. Derivative of arctangent of x is 1 over 1 plus x squared. And we're done, right? That's the derivative. What I refer to as the raw derivative. Okay. And this can't really clean up too much. And you'll see when I do the homework assignment, right? You'll see me kind of struggle to try and make my answers look like the back of the books. So I have to do some algebra. So in my homework solution video, you'll see me, try and massage these into better looking answers. But in this class right now, I'm not going to invest time in trying to clean that up. All right? I don't see much we could do. There's not a lot. I mean, I don't think that we could just put it all into one fraction maybe, but that's about it. All right, let's move on. Example 5. Were there any questions on that one? I said, remember, chain rule is important, right?
Since you said on your videos you'll do the algebra to kind of make it look prettier.
Yeah.
Will you accept what's the normal thing for us to do on the test? Like, do you want us to massage it, make it look prettier? Or if we just got all.
You'll always get more credit for the cleaner it looks, but part of it is you recognizing how much cleaner can you possibly make it. Like that problem right there. I want you to recognize there's not a lot you could do, right? It's just not a lot. So you would just leave it, maybe make it one fraction. So to answer your question, go as far as you can where you're comfortable with the simplification. Do the homework first, and then can we talk about it afterward? Like after you do the homework and take a look at what I did in the homework, you'll have a better idea of what I would expect you to do. Okay, this one's different. This one's different because,
Usually on his test, though, if he wants you to clean it up, it's pretty obvious.
yeah, I'll say it. I'll usually say, find and simplify. What's different here? X's and Y's are mixed together. You cannot solve for Y, which means you cannot get this as an explicit equation. It's stuck as an implicit equation, which means you must differentiate implicitly. So what we're going to do is we're going to find dy dx. We'll take the derivative on both sides of the equation with respect to x. So derivative with respect to x of the left side. And then we want the derivative with respect to x of the right side. That's our only option. So chain rule again is going to come into play here. What is the derivative of arc sine of this, of something? Arc sine of something. I always use the word something because
1 over that jump.
it's 1 over, okay, so the derivative of that is 1 over the square root of 1 minus that junk, that something, the argument, if you want to be technical, the argument squared, right? Does everyone understand where I'm getting that from? Anyone have a question on, like, where is that? Why is it xy squared? Everyone's okay on that? Yeah, that's considered the x. It's being replaced, right? All right, so that's good so far? So I now need to tack on with multiplication. I've taken care of the derivative of the outer function. The derivative of xy squared, which is a product, right? Multiplication. And I'm differentiating with respect to x, but I have to use the product rule here. Does everyone know the product rule?
Times the second.
So I'm going to use a set of parentheses. Now, I'm using a set of parentheses because I know that when I use the product rule, I'm going to get two terms. That's just the nature of the product rule. I'm going to get two terms. So I need that parentheses there. So it should be the derivative of this one times this one plus the derivative of this one times that one. That's the way I teach in my class. As long as you know the product rule, you should be safe here, no matter which class you came from. It's all the same rule. So what is the derivative of this one? 1, because it's with respect to x. So the derivative of x is 1 times y squared plus, now the derivative of y squared, this is the tricky one, 2y, y prime. So first power rule, the 2 comes down, right? 2 drops down, 2y to the first power. But then times the derivative of the base, the variable itself, which was y, which I'm going to say y prime. And that's it?
No.
Times x. So if I'm looking at this right now, I would agree with you if you told me, yeah, this is new, okay? You haven't seen this yet. You've never seen the derivative of arc sine before. But this right here should not be new to you. Okay, that was Cal 1. If I ask you to take derivative of xy squared with respect to x in Cal 1, we should all be able to produce this right here. That all right? Okay. Am I done on the left side? We did arc sine here, derivative of the inside here. We're done, right? Equals. Now, what about the right side? 2 terms, so derivative of 1 is 0, so I don't need it.
So then
Plus
product rule.
product rule again right there. So what is the derivative of x? 1 times y plus, now just derivative of y with respect to x, y prime times x. So there's your product rule on the right. And now what would you do? You got to solve for y prime. Which means
Divide by that.
distribute first to release the y prime from the parentheses. All right, I'm going to distribute. So when I distribute this fraction to this, I get y squared over root 1 minus parentheses xy squared squared. Right, that's just that y squared goes on top, right? Plus, now when I distribute this to this, all this junk goes on top, doesn't it? So we get, I'll kind of rearrange it, 2xy y prime. That's multiplication, so I don't care what order this is in. and then over root 1 minus xy squared, then equals y plus y prime x. All right. Any questions there? Now, the whole idea of getting the y prime out of the parentheses is so I can isolate it, get it by itself on one side of the equation. Yeah, I'm going to group it with the other one. So I'm going to take this one here and this entire term, and I need both of those on the same side of the equation. Doesn't matter which side I go to. So how about I leave this one here, bring this one to the left side, so subtract it over here, and then this one over here, let's move that to this side because it doesn't have a y prime in it, and then I will factor. Does this kind of ring a bell? Implicit differentiation, you have to factor. You have to get the y primes by themselves and factor out. Okay, so now I'm going to write down 2x y y prime over this root. I'm bringing this one over, so it's minus y prime x equals, this one was still on the right side, so y, but then minus, I'm bringing that one, y squared over square root of 1 minus xy squared. I'm almost there. Questions on that? It's just algebra right now. Now, the whole idea was that this has a y prime and this has a y prime, right? Two different terms, they both contain y prime. I can factor y prime out. So I pull a y prime out, times, now in parentheses I will have the 2xy over that root. And then over here, I pulled out the y prime, so all I have is the x left. And then equals this side. Ugh, okay, keep going. Now divide both sides by that big thing in parentheses here. So all of that divided by that right here, right? And then the same thing over here, the whole thing under there, like that. And then you have solved for y prime. And I'm going to stop right there because I only have 8 minutes and I have one more example to do. And then you could clean it up, all right? And I believe on one of my homework problems, I do the cleaning up of one of these. So go through it. Mm-hmm. Yeah, your algebra is going to have to be pretty tight here. All right, any questions on that? All right, the last problem is a related rate problem, which you did in Cal 1. A rocket is fired straight up with a speed, or velocity, 1,000 miles per hour. That's moving, okay? Constant speed. An observer who is a mile away from the launch point is tracking the rocket with binoculars. Right, so you see it, the rocket takes off a mile away. Someone with binoculars is watching the rocket. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? And then what is that in degrees per second?
So they want theta?
Close. Not exactly theta. They want to know how fast theta is changing. So they want like d theta dt. Okay, so there's the homework assignment. I'm going to work through that problem, but homework assignment usually appears at the end of the notes. All right, so
That's not the same as the schedule for lunch.
the schedule that you can print out for this class does not contain homework problems. It's all at the end of the notes, and that way if I need to change them, I can change them here. But that should be good. All right, so see if you can help me out with this problem. Now, this is where, again, we're going to get into some subtle differences between the classes. All right, how you learned related rates, and The way that I always taught my students to do them is to draw pictures first. I realize I only have like 5-6 minutes. And in my classes, what we did is we did kind of what we called like a general picture or something like that. And then we had the moment or instant, moment or the instant picture.
You have the given,
We find out what's given
or what you want.
and what we want. Those were kind of like the main themes of how we did related rate problems in my Cal 1 class. So in general, what we have is the ground, a rocket, and if you're, I've always told my class, if you're jealous of my artistic abilities, I've been doing this for years, okay? So if that's the best rocket you've ever seen, don't worry if you can't draw a rocket, all right? That's moving straight up. We have an observer over here,
Right up there with NASA concept art.
and he's got binoculars, all right? Again, don't be jealous of my binoculars, and the detail comes with time. How far away is this guy from the rocket? 1 mile from the launch point, right? So there is a fixed number in this, and that's the distance from here to here. That's 1 mile. I'm just going to put a 1 there. And we know that the rocket is moving straight up, and it has a speed of 1,000 miles per hour. So I'm not going to label the speed like as a side of anything. I'm just going to kind of write down 1,000 miles per hour, right? That thing's moving. And what I want to know is how fast the angle of inclination is changing, which means the angle between the binoculars and the ground. And we're not taking into account how tall the person is. We're just assuming that this is really a point on the ground. So if we look at this point going to the rocket and considering the rocket as a point, then this angle right here, theta, we're interested in something about that theta, right? How fast it's changing. But because it's changing, I'm not going to fix it. I'm going to leave it as a variable. The only thing not changing in this problem is the 1, right? And the speed. So that's my general picture. Now when I go to the instant I'm talking about, and you'd have to, we'd have to bring the word problem back up here. I believe I said when it's 3 miles high, right? 3 miles high, so I should probably draw this a little better. So I'm just going to use points instead of that. Now, tell me something. At this point, when the rocket's 3 miles high, this is still 1. Can you actually fix the theta now? Is theta fixed?
No.
If this is 3 and this is 1,
For that instant.
for that instant in time, that is a number, isn't it?
Yes.
Okay, I'd have to use my calculator to figure it out. I could use like an arctangent function, because what's tangent theta? What's tangent of theta? 3, opposite over adjacent. So if I know tan theta is 3, then I can do arctan on both sides and get the angle. But I'm not going to do that right yet. That's just my general picture. What am I given? What do I want? Velocity of the rocket. Now I'm going to come back to this picture, and I'm going to imagine that this is a point and that this is a side of this triangle, right? I'm going to label that side, let's call it y, because y usually goes up and down. Don't I know how fast y is changing then?
Yes.
So the given information of 1,000 miles per hour is actually dy, how fast y is changing with respect to time, dy dt. That's given to me. What I want to know is how fast what? The angle's changing. D theta dt is what I want to know, right? It's a question mark. At exactly the moment when what? When y is 3. Oops. When y is 3. So, I know the y value of this right triangle is changing, right? The y value is changing at 1,000 miles per hour. I want to know how fast the angle is changing, d theta dt, at exactly the moment that this y value is 3. Now, at this point in the problem, what we usually do is try and connect y and theta together, these two variables, y and theta. So you go back to your picture, and can you connect those two together? Come up with an equation that relates y and theta. You have to look at the general picture. You cannot go here. What would connect y and theta together? Tangent, right? And it'd be real nice. Tangent of theta is y over 1, isn't it? So now I'm coming up with an equation. I'm running out of room. My equation, I'll put it right here. My equation is that tan theta is y over 1, which is y, right? At this point, you could take the derivative with respect to time. And I'm almost out of time. You could, right? You could take derivative on the left side, take derivative on the right side. But this section is about inverse trig functions. So what I'd like to do in the last 10 seconds I have, it's actually going to take me more than 10. Don't write this down, but if I took derivative of this, I would get secant squared theta times d theta dt equals dy dt. That's what would happen if you took derivative of this with respect to time. Derivative of tangent of something is secant squared. The derivative of theta, because of chain rule, is d theta dt. Then derivative of y is dy dt. Yes? We're not going to use that, though. And the reason we're not going to use it is because in order to figure out your answer, which is d theta dt, you would need to know theta, wouldn't you? Which we could get, but it's too much work. Instead, here's what I'm going to do. I'm going to rewrite this. I'm going to take tangent inverse on both sides. Tangent inverse over here of y, right? What would happen if I do tangent inverse on both sides? You have theta equals tangent inverse of y, right? Use this equation now instead. Take the derivative of this with respect to time. What would you get? Derivative of theta with respect to time, d theta dt. That's clean. Now, what's derivative of arctangent of something? 1 over 1 plus the something squared times the derivative of the y, right? Which is dy dt. And now look, you want to know what d theta dt is, right? That's what you wanted to know. It's already solved for. And what are you going to need in order to figure out the answer? Dy dt, which you know, and y, which you know. And you never needed theta. See that? Much better way of going about a problem like this. But we had to have the inverse trig function to do it. Okay, I'm over already on my first day, sorry. I'll see you on Thursday. Do your homework. I expect that you are going to make an honest effort at your homework every time.
The one that's in the sheet, right?
Yes, the one that's, well, I